Hi guys, welcome again to another class in DSP design. As I promised last time, we are going to start a new series of DSP design on System Generator and then validate the design in Vivado on an FPGA platform. So the first class will be about FIR design in System Generator. Last time I designed an FIR in Vivado using the IP core, the Xilinx IP core. So you guys need to take a look, if you haven't, at this filter and how it was designed using IP core. So there is a detailed article about it on my website embeddeddesign.org, and also there is a video about it on my channel Embedded DSP Design. If you have not had a chance to take a look, please have a look to get an idea and a feel about how FIR filters are designed. So this tutorial assumes a prior knowledge about FIR design in terms of theory, and this tutorial is supposed to be just a bridge between the theory and the FPGA. So a lot of people know how to design filters on the paper, but to implement them in real life they find it challenging. So my goal is to bridge this gap. So let's get started. So the first thing you need to do, you need to open up your Simulink from System Generator. So System Generator is a licensed software. It's part of MATLAB. So you need to have that license so that you can implement designs on System Generator. Otherwise you won't be able to. You may have access to Simulink, but if you don't have System Generator license, you won't be able to. You'll be able to design it, but you won't be able to package it and send it to the FPGA, to Vivado, to use it on the FPGA. Okay, so you need to have a license. Make sure you have a license. So the first thing you do, you open a blank workspace and you start to collect the design blocks that we need for this tutorial. So the first thing you need to do is this guy here. This is called the token, System Generator token, and you find it right here. Click on this library here. It's called Library Browser. You click on it and you go to Xilinx Toolbox or block set, and then you click on Basic Elements and you grab this System Generator from there, and you grab this gateway in and this gateway out. So these are needed to sample your data inputs that you use for simulation, that you're gonna be using for simulation. So these are three important elements that you need to grab from this library, and then you close. So you need that. And then what do you need? We need this guy also. So we need the FDA tool. So FDA tool also same thing. You come here to the library browser and you grab it from there. And you need the FIR compiler. So same thing. You go to the library browser and you type in FIR compiler, and you should find it there, and you grab it here. So the first thing we need to do, we need definitely, when you want to design a filter, you have design specification for that filter. So with that in mind, you open the FDA tool from here, and this is how it looks like, and then you enter your design requirements. How much is your sampling frequency? In my case, the sampling frequency is 500 kilohertz. The pass band that I want a 25 kilohertz bandwidth filter, so the cutoff frequency will be 12.5 kilohertz, and I want a stop band of 20 kilohertz. So we put that in there. We want a noise rejection of minus 60 dB, so we put that in a stop. And we want a ripple of 0.1 dB. We selected the dB unit on the top, and the density of the filter, I did not touch it. That was the default value. And then I selected minimum order. Sometimes you may have some order in mind, so you specify the order. You can specify which order you want for your filter. And then on the list over here, you should select which type of filter you want. So in my case, I selected equiripple. It's a very common filter, and just for the sake of demonstration I used that. That's all. So you can select whatever filter you like. So once you are done with that, let's change this, make it 20 again, and then you will hit design filter, hit it again, and it takes, just my computer might be slow, it takes not even 1 second, and then you get your coefficients. So these are the coefficients. I mean, not listed, but this is the number of coefficients. We're going to have 167 coefficients. And if you want to see how they look like, these are the, click on this and you see them. So these are the coefficients. So for my case, I don't have to do much. I can just close this window and then go back to my design. But in some situation, you need to export these these coefficients. So if you need to export them, what you need to do, you need to go to here, File, and then Export. And then you can either export them to your workspace, and I set a name over here. I called it FIR underscore 25 kilohertz underscore bandwidth, and you hit export. Because it exists already, so we don't have to do it again. So anyways, and you go back to your workspace over here, and it should be there waiting for you. So it's here. So you click on it. This is the guy, and you can even list it over here. Let's see here. You click on here, so and they will pop up here. Sometimes you do that. Why? Because these coefficients are scaled. I mean, the gain of these coefficients are scaled to unity gain, so 0 dB, and sometimes you want more than that. It happened to me, for example, in some cases I had to replace some existing filter in our system, and if that filter, for example, has a 3 dB gain, so I have to make sure the new filter I'm going to be replacing it with has also a 3 dB gain. So basically here, this is your chance to adjust the gain of these coefficients, adjust these coefficients so you can have can match the gain that you are targeting. So that's what I'm saying. So sometimes you need that, and in that case you use that same variable that you used here into system generator filter, because in the system generator you need to specify the coefficients, and these coefficients have a label, and their label is this variable name. So this variable name is what you're going to be using in system generator to that would identify the coefficients. The other thing I like to do is, like here at the FDA tool, I export them as a text file. You go export here, and you export as a ASCII file, and then you hit export. It's going to ask you where you want to export them to, and you can specify the location you want them to be exported to, and it's going to be a file. And from there you can look them up and do something with them. For example, I did that already. I export them to a file, and then I brought them to my Excel, and I plotted the coefficients, how they look like, just to make sure that the structure I have here for this coefficient is symmetric. And this characteristic of being symmetric is important for me, because I don't want to do it. It's a good thing, because instead of having a lot double, it makes you reduce the number of multiplications by half, just because it's symmetric. So it's a very efficient way of processing the computation for the FIR. So when you have a symmetric structure, so this was the target. The target was I was aiming for a symmetric structure, and it turned out to be symmetric, and I validated that as I showed you here by plotting the coefficients. So anyway, so we go back here to the FDA tool. So once you export your things and you're done, you can either close this or leave it open. It's not going to make any difference. And then we go back to our system generator. So in our system generator, now we generated the coefficients. Great. Next step, we're going to come inside our FIR and do the right configuration. So the first configuration is here. So you need to tell the system generator where the coefficients are. So the coefficients, you specify them by this name. So the name you can see here, it's FDA tool, and this is the name of the tool. This name here could be different. You could have a different name. And that name, whatever name you use here, make sure you use it in the tool over here once you open it. Okay, and we have a number of coefficient sets. We have only one coefficient set, which is 1. And for the filter type, we are not doing any decimation. We are not doing any interpolation. So you just keep it at single rate. And the channel specifications over here, so we keep this to basic. We are not doing a channelized filter. However, in the future, I will show you how to design a channelized filter, a filter with more channels. And the last thing is the format. So we are doing input sample period, and you specify to here how many periods, sample periods. In my case, it's 1. So we are sending one sample at a time. And the next one is the implementation, how we want to implement this. So for example, here there's a few options. Some people select quantize only if you worry about the quantization. So for me, I want maximum dynamic range. I select maximum dynamic range, and I selected the number of bits I want for my coefficients width. I select 18. You could select 24, it depends on your application. And I selected here best precision fraction length. You could have some other value in mind. For example, you could have 20, for example. So this is based on your application. You can modify that yourself. And my structure is symmetric, as I showed you guys. And here the rounding. So the rounding here, there is a lot of options here you can select. So for myself, I just selected full precision. You could have selected, in my case, for example, symmetric rounding to infinity or to 0. So you can read about these ones actually in the manual. So I don't have time to explain each of them at a time, but for the sake of these demonstrations, I selected full precision. Okay, and usually I select, to be frank, I select symmetric rounding to infinity when I have a symmetric structure. Okay, the next step is this. This one you don't have to touch it, you just keep it to default. And the interface here, same thing, you don't have to touch it. These ones you can see here, T last and input, these are for channelized filters. You need them when you're doing channelized filter, but in this case you don't need them. And here the clock enable and the resets, they are user requirements. If you need them, you can do that yourself, that's not a problem. And that's it, nothing else other than this. And then you hit apply and then OK, and that's it. Okay, so this is it about the filter. So before we proceed, we need to come here to this token over here. It's very important, and we need to specify a few things. The first thing we would like to specify here is the clock. It's very important. At what clock are we running? So for my case, my FPGA clock I decided to use 200 megahertz. So here I specified how many nanoseconds for my clock frequency. I put, 10 to negative 9 divided by 200, sorry, 10 to 9 divided by 200 times 10 to 6. That's going to give you 5 nanoseconds. You could have just wrote 5 nanoseconds, but anyway, so you can do it whatever way you like. So here is the period. So this is the period. It's 1 over the running frequency is 1 over 200 megahertz. And you leave here, I selected this to be post synthesis for the analysis. So once you generate your IP, because you click generate after you when you want to generate it, you will, and after it gets generated, you will see a message that tells you, gives you the analysis in terms of timing, like did you meet the timing or not? Because sometimes your timing might fail because of your clocking, because your clock is too fast and you fail the setup time or even fail the whole time, anything. So you get a report at the end once your IP is packaged. And then you hit up. Before that, actually, you go here to the compilation and then you select your part number. So you select which FPGA you're using. So in my case, I'm using Spartan 7, so you click here and a list of FPGA names will pop up, and then you select which one you want, which package, how many pins, the grade, this kind of stuff. So I'm using this FPGA, so I listed that over here, and then you select the language that you want. I selected VHDL, and then you have to select the location where you want your IP to be stored. So I selected this IP to be stored in a folder within my Vivado project. And once you do that, so here you don't have to do anything, it just default. Once you do that, you go back to compilation again and you hit apply, and then you generate it. You hit generate. When you hit generate, it takes about 5 minutes to generate the IP for you. And if the IP generated successfully, you will see it, and you will look also at the timing report. And if the timing report has passed, it's going to show pass in green. Otherwise, it's going to show you failed in red, and then you have to go back and see why it failed. It gives you why it failed, it gives you which path failed, and then you have to investigate that path and adjust your timings and till you pass the timing requirements. And that should be it. So close this. So here we're gonna be simulating two frequencies. I'm gonna be adding a 1 megahertz onto this is a sine wave generator onto I believe 5 kilohertz. Yeah, it's 5 kilohertz. So we have 1 megahertz on top of 5 kilohertz, and we'll run that through our filter and see if the filter will filter out the 1 megahertz frequency or not. These blocks are very important. These are called the gateway in. So the gateway in this case is we are sampling at 500 kilohertz, and it's Boolean, so basically it's either 0 or 1. So this tells the FIR filter that this input you are looking at is valid or not. So that's why I did this high for this pulse frequency rate at 500 kilohertz. This is just for the sake of demonstration. However, into the Vivado, you don't do it this way, or at least I don't do it this way. In the Vivado, you would have to make sure that your pulse, of course, is coming at a frequency equal to your sampling frequency, and not only that, that pulse, it needs to be high for only 1 clock cycle, and 1 clock cycle of the filter, because the filter has a clock, has a clock, and the filter runs at a higher frequency than the sampling. So, for example, I have a sampling of 500 kilohertz, but my filter is running at 200 megahertz. So that's because it's processed a lot of computation, and it needs to finish before it can process the next sample. So that's why it has to run at a higher frequency. So for the sake of that, I have to make sure that the sample is high only for 1 clock cycle, so that the filter see it only 1 time. If the filter see it for 2 times, let's say if you keep your pulse high for 10 nanoseconds, the filter will see it twice and will think it's a new value and will process it, and then the output will be wrong. So don't do it this way. The T valid has to be high for only 1 clock cycle of the filter clock. And this is the data that's coming. You put also a gateway for it, and you specify the frequency, and the frequency for that is 500 kilohertz, and you specify the bits of the samples. So in this case, I have an 8-bit ADC, so I configured that one as an 8-bit ADC. So the total bits, we have 8 bits, and we have 7-bit fractional, and it is the type of data is 2's complements, so it's signed value basically. And you close that, and you add these at the output if you wanna check the data output on a scope. So this is a scope also you can get from the browser from here, and it lets you look at the data how it looks like. So let's quickly run this this simulation here, just to let you know how it looks like, show you how it looks like. I hope it won't take too long, because I don't want to. It's running now. Okay, so quickly take a look here. So it's running. Let's go back to it. I just want to look at the noisy signal here, how it looks like. It's not gonna look nice, it looks terrible actually. You can see that. Let's see here. Very noisy, as you can see. And then let's see how it looks like at the output here of the filter. So it looks nice, looks clean, apparently nothing yeah. So yeah, so that's pretty much it. So if we are happy with our design at this point, then we can package it and send it to the FPGA. So stop it here, stop. So now, as I said, you come here, open this. Once it opens up, you hit generate, and then it generate the IP for you. And you go now to Vivado. So now in Vivado, I'm going to go to Vivado now, the IP generated. In Vivado, what you need to do, because I added that already, so that I can save time and don't make this video too long. So in Vivado, you go here, you go to this plus sign here. So assuming you have your projects, you set up and everything, you go to the sign over here, and you look here, create a design, so design resources or sources, and you go next over here, and then you add file, and then you go and you look for the location where you saved your thing. So I saved it here. at this folder over here, and you can keep coming all the way to the IP, and then you click on this, and then it's going to open up, and then you look for a file called XCI. So here, by the way, I changed the name, so you can change the name if you want. So I changed the name of it, so it was not, when I package it, was not named like this. Over here I changed the name, so you can change the name over here, and then you hit OK, and then it's going to be added into your IPs over here. So on your IPs over here, it's going to be shown as a red, in a red color. So you right hand click on it like this, and then you go at report IP status and you update it, and it's going to open up, and then you can look at the like here you can open it and you can look at the configuration, how it is done. I might post a video maybe in the middle of the week or so that explains or show at least how to export the IP, because it's it can be not that straightforward, but anyways, hopefully it won't be for you guys. So once you open the IP, you don't have to change anything, but you might, I don't know, but this is how it looks like. So it has the number of coefficients we have, exactly what we expected. This is the configuration if you guys remember, we entered in the configuration of the FIR compiler. So dynamic range, if you guys remember, 18 bits, symmetric. So all this information is here. So we'll be waiting for you. And that's it. And sometimes, I don't know, if you need to add and forget to add a reset, you want to add it again, you can come here and do it. But for my case, like I'm seeing here, like here you can change these and then repackage the whole thing again if you need to. But anyways, so this is the summary. It gives you also a summary of the filter. So all this stuff is handy. That's it. So the thing here, what you need to get from this after you export it, you need to come to the instantiation template and you need to open this file, and this is all you need. You open this file over here. Now it's open for us, and we need to take the instantiation. So this is the instantiation of the filter. This is our filter. We have a clock, we have a T valid, we have to tell the FIR this input is valid or not, and we have data inputs. And this T ready, it just always high, I noticed, it just tells you that the FIR is ready. And this is T valid when you have an output from the FIR. Whenever the FIR output a certain sample, you get a pulse, of course, that's high for 5 nanoseconds. And this is your data. So data in my case is 32 bits. However, I don't need 32 bits, so because I have a DAC and I'm planning to do a demonstration sometime mid next week about the performance of this filter, I'm just taking 12 bits. So I quickly go to because I don't want to make this video too long, quickly I'm going to go to the code and show you what I exactly did over here to simulate the performance of this filter. So I have two DDSs, two components of DDS. I explained in my previous video how to instantiate or how to design a DDS on Vivado. You can take a look at the video to understand how is that. So I have one that generates 1 megahertz, and I have one that generates 5 megahertz, and I have another that adds these two frequencies together, and then I feed that into my filter, as you can see here. And I'm gonna show you the filter instantiation here in terms of signals, what signals comes here. Yeah, these are the ones. So yeah, so we have T valid. So this T valid, again, as I said, is I control that, I generate that at a frequency of 500 kilohertz, and I make this sample high for only 5 nanoseconds. I will show you down how it is done. This is just an output, I'm not worried about it. So this is the input. So my input, when I added the two signals, turned out to be in 9 bits, so I need only 8 bits, so I go from 8 to 1. And the T valid, this is an output. Whenever a valid output, you get a pulse, and this is our data. So the data is 32 bits. However, I took only 11 bits out of it. I think he did. Yeah, I did over here. I have this variable called FIR out, and I took only 12 bits from it. Okay, and I show you how I generated the valid pulse. The valid pulse, I have a frequency of 200 megahertz for this process, and I have a counter that counts up to 400, and that's how I generated this pulse. So this gives me a frequency of 500 kilohertz. However, the pulse is high for only 1 clock cycle of 200 megahertz. So that's pretty much it. I'm sorry if I'm too quick on this, but if you have any questions, please feel free to share with me. So the simulation looks like this. As you can see, this is the this is the mixed signal. This is the noisy signal, 5 kilohertz plus the 1 megahertz, very noisy. and this is the filtered signal. You can see there is a delay here that's expected. There is something called the group delay. So the group delay of an FIR is half the sampling frequency times the number of taps. Like in our case, the number of taps is 168. So basically you take 168, take half of that. That's going to be 84 times 5 nanoseconds. That's going to give you the group delay. So the group delay is 84 times 5 nanoseconds. So that's our group delay. So that's pretty much it in terms of how to design an FIR filter in System Generator and how to export it into Vivado. I really hope this was beneficial and you learned something from it. And as I said, in the mid of next week, I'm going to be doing a quick demo for this filter on the hardware. I have an ADC that samples data, and I have a DAC as well. And I'm going to be using my spectrum analyzer and a frequency generator, and I will come up with something to show the performance of this filter I designed. And after that, either you guys suggest some videos you want me to cover for next week, or I come up with my own videos. But probably the next video would be how to design a 2-channel filter, FIR filter. So this is 1 channel, so we do 2-channel, and then we can do multi-channel, and after that we can move to DDS and move to modulation and go over the list that I posted on my channel before. So it's gonna be a longer series of DSP design on System Generator, and how to export this design from System Generator into an FPGA platform and evaluate them and design, DSP systems. So again, thank you for watching, and another time, and until then, take care. Bye.